Throughout the technological development, people were creating new things by having the same foundation. And in this foundation, starting from chips to big machines, every little things have their own task, and these tasks are sorted in the given environment, which works smoothly. But what if one time the environment fails? What will be with the tasks that are so needed for simple work of the machines? That's what we're trying to solve. A distributed embedded system is a set of nodes which consist of tasks that cooperate to achieve a common goal. But to adapt to a changing environment, the system needs to be able to change its own configuration.
To achieve this, we use reinforcement learning. The main elements of a reinforcement learning system are the agent or the learner, the environment the agent interacts with, the policy that the agent follows to take actions, and the reward signal that the agent observes upon taking actions. Reinforcement learning can solve complex problems that cannot be tackled with other machine learning algorithms because it focuses on the problem as a whole, does not require a separate data collection step, and it operates in dynamic, uncertain environments. The components of our reinforcement learning model are shown in this figure. In observation space, we have the tasks, the nodes, and the critical masks for the critical tasks. Whenever we start an episode, we take a new observation and a random action. If the task is valid, we then check if the node is valid. That is, if the task can be allocated to a given node. If it's not possible, we end the episode. As we can see, tasks 3 and 5 are critical tasks. There are 2 copies for each of these tasks. Also, you can see the critical masks of these tasks, which are represented as 1s and 2s. For building such a complex agent, we use LSTM-based actor-critic model to learn behavior of the reconfiguration and update our policy using PPO to maximize our rewards.
So after discussing all of the things, how did our agent actually perform? What are the results? For a lower number of tasks with static weights, our agent performed very well, reaching 100% success rates in its very early stages. However, when we add some variability to our task weights, the model does not learn as fast as learning before 200,000 steps. So that's why we utilize curriculum learning, the blue line here, to reach the same 100% success rate within the first 250,000 steps as compared to the normal approach which would have normally taken more than 350,000 steps for learning an environment where the tasks had variable weights. Additionally, here a web demo, our first CADES implementation contained only a bin packing algorithm where we'd simply pick the task at any time and allocate them to a node. However, in our new simulation, now we have critical items and their masks. So this is critical item 1, this is 2, and these are their duplicates. We must allocate the duplicates and the main critical item in separate nodes to ensure that in case of node failures, our system prevails. So now we have also considered allocating critical items, and we have additionally made sure that no duplicate of the same critical type are allocated in the same node as shown in this WebUI demo.
So what impact do these systems have on the world? The CADES optimize operations in real time, leading to significant improvements in efficiency and productivity. For instance, in manufacturing, these systems can adapt to changes in production demand or equipment status, reducing downtime and waste. Also, in critical applications such as automotive safety systems or healthcare monitoring devices, for example, they can adjust to varying conditions to maintain optimal operation, reducing the risk of failures or accidents.